Today we'll be talking about network layer protocols. Uh, the network layer in version 4 can be thought of as one main protocol and three auxiliary protocols. So we have one main protocol and three other auxiliary protocols. The main protocol is the IP protocol, or IP version 4 when we are talking about the version 4 protocol. So IP is responsible for packetizing, forwarding and delivery of a packet at the network layer. The other protocol is Internet Control Message Protocol, which is called ICMP, and again version 4 because we are talking about the version 4 IP. So the Internet Control Message Protocol, ICMP, helps. So it's an auxiliary protocol. It helps IP version 4 to handle some errors that may occur in the network layer delivery. Okay, so it's an auxiliary protocol. The main protocol is IP, or Internet Protocol. There is also the Internet Group Management Protocol, IGMP, and it's used to help IP version 4 in multicasting. We'll see some examples of ICMP ICMP version 4, and we've studied already the ARP. The other auxiliary protocols, these are three auxiliary protocols. The other one is the Address Resolution Protocol, which we studied before when we studied MAC address to IP address resolution. So ARP is used to glue the network layer and data link layer in mapping network layer addresses to link layer addresses. Okay. So we need ARP to. It's a network layer protocol. It provides services to layer 2, or the link layer, as we studied before. So the main protocol, as I said, is the Internet Protocol. Position of IP and the other network layer protocol in the TCP/IP suite. So this is you see IP, this network layer, and these are the three auxiliary protocols, and this is the IP. So IP works in layer 3 together with ARP, ICMP and IGMP. As I said, ARP provides services to a data link layer. ICMP is used to provide some error message communication, and we'll use we'll see some examples of ICMP. So the main protocol, as I said again, is the IP protocol, or Internet Protocol. IP version 4 is an unreliable protocol. So what is meant by unreliable? The term best effort is actually sometimes we call it best effort delivery service. Best effort means that IP version 4 packets can be corrupted or be lost or arrive out of order or be delayed and may create congestion for the network. So IP is not responsible for these problems. The packet can arrive corrupted or it may be lost and IP will not try to deliver it again, or they may arrive out of order. IP will not involve in reordering these packets. So these problems are actually handled by other layers. So in case of TCP/IP, TCP can handle, for example, if a packet is or a datagram is corrupted, then it can request it to be resent. If it's not delivered, it can of course ask for it to be re-delivered, or it can reorder if they are out of order, and so on. So IP is a best effort delivery protocol. It's not a reliable, but TCP is a reliable protocol. Packets used by the IP are called datagrams. So when we talk about IP packets, we call them datagrams. IP version 4 is also a connectionless protocol. At the beginning of this course, we studied connection-oriented and connectionless. So IP is connectionless protocol. That means if you have two paths or several paths from source to destination, packets or IP datagrams can, some of them go through this path, some of them go through the other path, some of them. So it's not connection oriented, it's connectionless protocol. This means that each datagram is handled independently, okay, and each datagram can follow a different route from source to destination. This implies, of course, that datagrams sent by the same source to the same destination could arrive out of order, because maybe the delay across this path can be higher than the delay across this path. So you may send a packet on this route and the datagram another on the other route. Although you send this first and then you send this second, maybe this will arrive before this one because there is high delay on this path. So they will be out of order. Of course, as we said, IP does not handle this problem, but TCP can reorder them and place them in the correct order. The datagram format of IP is something like this. We have a variable length header of a size from 20 to 60 bytes. Okay, so the length of the header is variable, minimum 20, maximum 60 bytes. Okay, and then we have the payload. The payload, of course, is also, you can it's not of the fixed size. You can put up to 65,535 bytes total in an IP datagram. That's too much, actually. If you remember the Ethernet, we'll talk about it later. We only have 1500 bytes maximum size. Therefore, if you compare this with this one, it's much bigger size. Okay, so the header, this header is something like this. Okay, now we'll talk about each of these fields in this header. Each of these fields in the IP version 4 header. Okay, this is the header. It can be 20 to 60 byte. 20 minimum. You should have these. Okay, so these are 20 bytes, and another 40 bytes, which are options plus padding. So you may have them and you may skip them, not have them. For example, you remember the minimum size for Ethernet size. The Ethernet size was what? Minimum size, you can tell me. You can remember.
64 byte.
That's the minimum size. Are you sure? 46. أنا 36 byte. So if for example you have a packet with only header and some 5 byte, for example, so 20 and 5 byte payload, it's less than this, so you have to add some padding here to make it the same as the minimum required by the Ethernet. So padding is just some extra nothing you can add just to make the size. We talk about it in this lecture again. So version number here, first field is version. Version is 4 bits, and of course obviously it's the IP version. If it's IP version 4, then this value is what? 4. Header length, this is 4-bit header length field. So this is 4 bits, the field, and defines the total length of the header, datagram header, in 4-byte words. Okay, so this will tell the total length of the header in 4-byte lengths. So we have here maximum chanda. What's the maximum header size? 60 byte. If we talk about 4-bit lengths, as we said, 4-bit header length, then we need how many bits? We need only 4 to represent up to 64, because 4 would make 16 times 4, which is 64, and the maximum size of the header is only 60, so we can use the 4 bits to represent the total header length. Why you need to know the header length? Because the header length is not fixed. So maybe it's 20 or maybe 21, maybe up to 60. You need to know when the payload starts. So you need to know the header length so that you can know when the payload will start. Therefore, we need the header length. The service type here, this field, is 8 bits, and it was used to be called a type of service, but now It's called diff services, and you can use that field to give some differentiation to packets when you want some different treatment for a packet. Then you can use this field. For example, you have a packet that you want to be delivered uh, over if you have priorities on your network, or you can use this field uh, to give some precedence or uh, priority to your packet. Maybe some routers will use along the path will use this service, but some of them don't have the service, so they will not do any difference to the packet. They will treat it like a normal packet. Uh, Total length. This 16-bit field defines the total length. Here you see we have header and data. This was only header length. This is the total length, which is header plus data of IP datagram in bytes. Okay, a 16-bit number can define 2 to the power 16, which equals so this is the maximum length of the packet of the IP datagram. We said this is the maximum because we have total length 16 bits. Okay, so 2 to the power 16 is the maximum length that we can maximum IP datagram length. This field helps the receiving device to know when the packet has completely arrived, because you know now when the data started because you know the header length, but when the payload ends, how you know that? You can use the field total length, so you know when the packet is completed, when you receive all the bits or the length of the packet defined in this field. So if a packet is corrupted and you didn't receive the size in this field, you know that some data has been lost during their transmission, and then you can report that, or you can we see later what we can do. For example, the Ethernet protocol has minimum length and maximum length restriction on the size of data that can be encapsulated in a frame. So we said minimum is what, 46 bytes to 1500 bytes. If the size of an IP version 4 datagram is less than 46 bytes, some padding will be added to. Why we need the padding? Why we need the padding? So that we make the packet size at least 46, so that it can be accepted by the Ethernet to achieve the minimum frame length requirement. In this case, when a machine decapsulates the datagram, it needs to know to check the total length field to determine how much is really data and how much is padding. So you have the total length field and you have the header length. Okay, of course we said the header length in 4-bit words. So we'll have to multiply this by 4. So this is the length of data, and the rest is what? Padding. Okay. We have another field, identification, flags, and fragmentation offsets. You see here the maximum size is 65,000, say, bytes, and the Ethernet maximum size was 1500 bytes. So if you have, for example, a packet IP datagram of, say, 6,000 bytes, is that possible? Because you can go up to 65, and you want to send it over Ethernet. Ethernet does not support this size. What you have to do, you have to fragment this. You have to fragment it at least to how many packets? To 4 packets of size 1500. 4 of these packets. Okay, so what you can do here, you can fragment it, but then you have to know which one is the first fragment, which one is the second, which one is the third, so that at the receiving end you can combine them to restore the original packet. So that's the responsibility of this field, the identification, the flags, and fragmentation offset. These 3 fields are related to the fragmentation of the IP datagram when the datagram is larger than the size of underlying network technology. Okay, so in this case you have to say, for example, this is the fragmentation offset. At when you exceed this, I need to fragment the packets, and the details of these fragments are included in this field. Okay, so this is related to fragmentation. Okay, we have an important field is TTL, time to live. When you use ping, you've seen this TTL field. So what is TTL, or time to live? TTL is like a flag or a field that you set up when you send the datagram, and you'll tell the routers that if this field is 0, then stop circulating them, circulate the packet. Due to some malfunctions of routing protocols, or some routing protocols may function in wrong way, malfunction, a datagram may be circulating there in the internet. So if there is no other way to stop the datagram, then it will circulate forever. Okay, so if there are many of these packets circulating, then they will create lots of extra traffic. TTL is actually provided to control the maximum number of hops visited by a datagram. So when you say TTL is 120, for example, each router, when your datagram visits a router, this will be decremented. So when you first visit a router, it will be 119. Next router, it will become 118. Next router, it will be, until maximum of 120, it will be 0. So when this is 0, any router that receives a datagram with a TTL of 0 will just discard it. It will not route it anymore. Okay, so it will stop being forwarded to other routers, and because its time to live counter is reaching 0, and it will stop. This way you can control how many number of hops this packet or datagram can travel. So now we understand what is time to live. Now there is another field, is the protocol. So if we go back, this field is 8 bits. It's the protocol field. So each protocol that uses the IP service has unique 8-bit number inserted in the protocol field. So if a protocol, for example, is ICMP, this field will be 01. If it's IGMP, it will be 02. So what protocol? So this payload belongs to UDP. Then the field, protocol field, UDP is 17, so that field will get value of 17. If the payload is of a TCP protocol, TCP is 606, so the protocol field will be 06. And if it's ICMP, for example, or IGMP or whatever protocol, each protocol has its unique 8-bit number. Okay, so this will tell us the payload is from which protocol, or what protocol provided this payload. When the payload encapsulated in a datagram at the source IP, the corresponding protocol number is inserted in this field, in the protocol field. Okay, so you are sending the data. You are using UDP, for example, at transport layer, and you send your data to the network layer. The network layer will know that UDP sent this payload, this, because you see there is header here. When you send data down, you'll add, of course, TCP header, but all the data will be payload for the network layer IP protocol. Okay, so here is the network layer header. Here is the TCP header. The TCP header together with the payload, TCP payload, will be payload for the IP protocol. Okay, because it will IP will use its own header, which is this one as we seen. When the datagram arrives at the destination, you'll check the protocol field, and you know, for example, you see protocol is TCP. The field is 06, so you know this payload came from TCP. So you'll forward this to TCP. You'll not forward it to UDP or other protocol. So this is like multiplexing and demultiplexing. The other field is header checksum. So we have, after the protocol, we have header checksum. IP, as I said, is not a reliable protocol. It does not check whether a payload carried by the datagram is corrupted during the transmission. IP puts the burden of error checking of the payload on protocol that owns the payload, such as, for example, UDP or TCP. They can check if their payload is okay or corrupted. The datagram, however, the IP datagram header contains a field called header checksum. And its error checking is the responsibility of IP. Okay, so we have this header checksum, and we can use it to check if there is an error with the packet, or there are some chunks of the packet or datagram missing. We can use this header checksum. Errors in the IP header can be disaster. Why? For example, if the destination IP address is corrupted, the packet can be delivered to wrong host. That's a problem. For example, if there is some packet that you want to contain some, for example, you are communicating with your bank account, and the destination address corrupted, you forwarded your data to wrong address. Maybe you'll be in your data may be used. So if the protocol field is corrupted, as I said here, for example, if, for example, instead of the payload was originally from TCP 06, but now because of some error 06 changed to 02 at the receiving side. So you are going to deliver this payload, instead of delivering it to TCP, you deliver it to what? 02 is which is IGMP. IGMP maybe cannot deal with this payload, and it will be useless. So you may deliver it your data to the payload to the wrong protocol. If the fields related to fragmentation are corrupted, the datagram cannot be reassembled correctly, because as said, when we fragment a datagram, we use IDs. For example, this is 6,000. I fragmented to 1,500 bytes so that I can send it over the Ethernet. So I label these fragments 1, 2, 3, 4, for example, so that if they arrive out of order, for example, 1 arrives, then 3, then 2, then 4, but because I have these IDs, I can reorder them and then combine them to create the original payload. But if these IDs, for example, there were errors, I may not be able to reassemble the packet correctly so that I recover the original unfragmented data. And that's also a problem. IP adds a header checksum field to check the header but not the payload. So you see, it's called header checksum. We are only concerned if the header is okay. So you check, you know what is checksum. You studied, I think, checksums before. So checksum is some like operation done on these data. You'll get a value when you do some math, for example, exclusive ORing or whatever. For you studied parity bits, for example. So parity bits are a sort of checksum. So for example, when you say there is even number of zeros or even number of ones in this header, if this number is changed, then you may expect some error happened. So that's sort of we actually, I think, CRC, cyclic redundancy check some errors are used, checksums are used in this protocol. So what you do here is you calculate the checksum at the sender and insert it in the field header checksum. At the receiver, you again calculate the checksum of the header and compare it with the received checksum. If they match, you say this packet is delivered correctly. Not the header. We are talking about header checksum. So maybe there is problems with the payload, but we are just concerned about the header checksum here. But if the CRC does not match the received CRC with the calculated CRC, they do not match, then you say this is there is an error with this header. This header is corrupted. As the value of some field such as TTL may change, you see here TTL, as we studied before, routers when it was 128 at the beginning, then arrived at one router, then it was 119. So this TTL is a field in the header. You see, TTL here is a field. So if this field changed, a router changed this field, then the checksum also, this CRC will change. So each router should recalculate the checksum, header checksum, and insert it here. Okay, so this actually is some burden, yani it's some load on routers to do this every time. The checksum needs to be recalculated at each router because we may change some fields in the header so that the checksum also will change. IP datagram format, source and destination addresses. We studied this. These are, of course, the IP addresses of the source, which is in case of IP version 432-bit, and IP of the destination. So the logical addresses of the source and the destination. Sometimes you don't know the IP address of the destination. In this case, you'll use a DNS service, which is an application layer protocol that provides services to the network layer. So you remember ARP is network layer protocol, provides services to the data link layer. DNS is application layer protocol, provides services to the network layer. We have another field is options. You see, options can be from 0 to 40 bytes. And from its name is options, so it's optional. The packet can have the options and may not also. A datagram can have up to 40 bytes of options. Options can be used for network testing and debugging. Although options are not required, they are optional. Option processing is required by any IP software. So if any net router processing the datagram, if there are options, they should be able to process the option. Although options are optional, but if they are used, then you have to process them. This means that all implementations must be able to handle options if they are present in the header. The existence of options in a header creates some burden, of course, on the datagram handling. Some options can be changed by routers, which force each router to recalculate the header checksum, like TTL, for example. Payload, of course, you know, payload is the original data that you want to send. But actually, you see, if you have payload here, this payload is IP payload, but it's actually the full TCP IP uh, packet. You see, for example, this is TCP header and this is TCP payload. So all together will be the payload of the IP. Okay, so payload is coming from upper layers. It by itself can contain headers of upper layers, but it's all payload for this layer. We talk about the MTU or maximum transfer unit. You see, the Ethernet, for example, supports a maximum of 1500 bytes, but maximum length of IP is 65,000. So if you have a packet, IP packet bigger than this size, you should fragment it. How you fragment it? You fragment it into several datagrams, and you identify each one so that you can reassemble at the receiving side. When a datagram exceeds the size, exceeds the MTU of the underlaying, for example here, this one exceeds this size of the Ethernet, because you are going to send this datagram over some technology, for example, Ethernet, token ring, whatever. So each one has its own maximum size, MTU size, maximum transfer unit size. So if this is greater than this, then you have to fragment it. Normally, you are not going to use this big size of packets, but IP supports this big size. Normally, we'll use sizes smaller than 1500 so that we not do fragmentation, but maybe you can use some bigger size packets so that you can, for example, get better performance of the network. The payload of the IP datagram is fragmented. However, most parts of the header, with the exception of some options, must be copied to all fragments. So when you fragment, the payload is fragmented, okay? But the header will be almost same, except some fields will change. For example, so if this payload is to be fragmented, they will all use the same header, except, for example, here, which thing can be different. Source and destination addresses would be same. Header checksum would be because it's same header maybe, but sometimes these are different. These things and header checksum. So other fields will be the same for all fragments. So if you fragment it to three parts, all the three parts will receive a copy of this header, but with these fields changed. So identification of the fragment, for example, flags and fragmentation offset maybe. Then if any of these fields change, of course you need to recalculate the header checksum. The host or router that fragments datagram must change the value of the three fields, as we said: flags, fragmentation offset, and total length. The rest of the fields must be copied. Of course, the checksum also must be recalculated, because if you change any field in the header, the checksum will change, so you need to recalculate it. A fragmented datagram may itself be fragmented if it encounters a network with even smaller MTU. Sometimes, for example, you fragmented this to fragments of 1500 bytes, but then during transmission over the network, there is a technology, for example, a frame relay. Frame relay does not support this size of MTU. So it will fragment this even to smaller fragments, for example 64 bytes, so that it can send it over its technology. So fragmentation can happen at different levels and different states. A datagram can be fragmented by the source host or any router in the path. The reassembly of the datagram is done only at the destination. When you fragment, you can fragment at the sender, for example, or a router, because it does not support this size, MTU size. It can fragment it. But to defragment or recombine the fragments is only done at the destination, because no one else is going to use these fragments. Only the destination, intended destination, this one, is going to assemble the fragments. The header of IP version 4 datagram is made of two parts: the fixed 20 byte and the options, which are of maximum 40 bytes, in multiples of 4 bytes actually, to preserve the boundary of the header. Options are not required, again, as we said, but they can be used for network testing and debugging. Although they are not required, but option processing is required. This means that all implementations must do this. I think we already mentioned this. Options can be divided into two categories: single byte and multiple byte options. So we have two categories, two broad categories: single byte and multiple byte options. There are two single byte options: no operation. A no operation option is 1 byte option used as a filler between options. So when you have several options, you can use this as a filler between them. End of option. An end of option is a 1 byte option used for padding at the end of option field. It, however, can be only used as the last option, so you cannot use this at any other. The other type of option is multiple byte options. There are 4 multiple byte options. The record route, you see here. So if you have this option enabled, used to record the internet routes that handles the datagram. It can list up to 9 router addresses. It can be used for debugging and management purposes. So when this option is enabled, it will list up to 9 router addresses that the packet went through. Okay, so you can use this option to know how this packet traveled from source to destination. The other option is strict source route. Strict source route is used by the source to predetermine a route for a datagram as it travels through the internet. Okay, so when you say strict source route, it means you can do some control over the route when you send the datagram. Dictation of a route by the source can be useful for several purposes. The sender can choose a route with a specific type of service, for example, such as minimum delay or maximum throughput. Alternatively, it may choose a route that is safer or more reliable for the sender purpose. For example, you can choose to prevent some routes that are not secure, for example. If a datagram specifies a strict source route, all the routes defined in the option must be visited. So if you define a strict source route, you have to visit all the routes or all the routers defined in this option must be visited. A router must not be visited if its IP address is not listed in the datagram. You see? So if the datagram visits a router that is not in the list, the datagram is discarded and an error message is issued. So this can be useful when you have security concerns. You don't want your packet to go through some routers. You can use the strict source route. This is very important option when we deal with IP security. If the datagram arrives at the destination and some of the entries were not visited, it will also be discarded. You see here, you specified, for example, 5 routers in the strict source route option. And when it arrived at the destination, it didn't visit all these 5 routers. It visited only 4. So it will also be discarded because it didn't go through because this is a strict source route. There is another option which is a loose source route. A loose source route is similar to a strict source route, but it's less rigid. Each router in the list must be visited, but the datagram can visit other routers as well. So the ones in the list, you should visit them, but you can also visit some other routers. Okay, but here in the strict source route, if a datagram visited a router not in the list, it was going to be discarded. We have also the timestamp. A timestamp option is used to record the time of datagram processing by a router. So you can know when this processing happened. The time is expressed in milliseconds from midnight, Universal Time or Greenwich Mean Time, GMT. Knowing the time a datagram is processed can help users and the managers track the behavior of the router in the internet. Sometimes there is a high load at some points, so you can, if you have this time, you can track the behavior of these routers and see when they are loaded, when you can prevent going through those routers if they are, for example, overloaded at some times of the day, so that you can choose different routes. We can estimate the time it takes for a datagram to go from one router to another. We say estimate because although all routers may use universal time, their local clocks may not be synchronized. You see, they may not be, their time may not be totally accurate, so that's an estimate. Now we finished the main protocol. We'll study also, as we said, ICMP. We studied ARP and an idea maybe about IGMP. So the other protocol is what? ICMP. And we have also version 4 and version 6. As we said, IP is not reliable. It's best effort protocol. It has no error reporting or error correcting mechanism. But ICMP actually helps to report or to do some about this problem. What happens if a router must discard a datagram because it cannot find a route to the final destination? So you received a packet, a router received a packet or datagram. Its final destination IP address is not in the router's table. What it can do, the router? It doesn't know how to forward it. So it should be able to communicate that it does not have the route to the destination. Maybe also because the time to live field is 0. Okay, we said the router will decrement time to live when it visits a router. The time to live will be decremented by 1. Now the time to live reached 0. This router decremented, it was 1, now it's 0. So what it can do, it is not going to forward this packet because its time to live is 0. What happens if the final destination host must discard the received fragment of a datagram because it has not received all fragments within a predetermined time limit? For example, where you have a packet, you fragmented that packet or datagram, and then at the receiver side, you didn't receive all the fragments, you just received some of them. So what you do? Here we need the ICMP for these cases. These are examples of situations where an error has occurred and the IP protocol has no built-in mechanism to notify the original host. The IP protocol also lacks a mechanism for host and management queries. A host sometimes needs to determine if a router or another host is alive. You remember when we used ping, we used ping to check if another computer is on and responding, or you can use it as well to check a router is on and responding. So that's another mechanism that we can use ICMP to do that. And sometimes a network manager needs information from another host or router. You want to check this router is working or not. So you can use, actually ping uses ICMP version 4 protocol. The Internet Control Message Protocol version 4, ICMP4, has been designed to compensate for the above two deficiencies. It is a companion to the IP protocol, so it helps IP protocol with these situations. ICMP is a network layer protocol. Okay, so it's a network layer protocol, but its messages are not passed directly to the data link layer. Instead, the messages are first encapsulated inside IP. So ICMP version 4 is encapsulated into IP datagrams before going to the lower layer. When an IP datagram encapsulates an ICMP version 4, the value of protocol, as we said before, is set to 1, as we here. So if it's ICMP, it will set the value of the protocol to 1. To indicate that the payload is an ICMP message. ICMP messages are divided into two broad categories. We have error reporting messages and we have query messages. We used these, you'll remember now when we talk about them. Error reporting messages are used to report problems that a router or a host destination may encounter when it processes an IP packet. Query messages, which occur in pairs, help a host or network manager get specific information from a router or another host.